Okay, so this is lecture 23, and our goal here is to try to abstract what we've been doing for surfaces in 3 dimensions to a slightly more general context, all right? So here we want to give some description of a surface that's divorced from the 3-dimensional context, all right? So to start with, we'll talk about an abstract surface. We might call it a surface without geometry. That's what O'Neill calls it at various points in the text. And so basically it's just some set, all right, together with a collection of patches which cover the thing. And of course you have to have this compatibility, smooth compatibility condition. You need that the, when patches overlap, they give you smooth transition functions, right? Smooth in the sense of usual advanced calculus. And so that gives you what you call an abstract surface, or a surface without geometry. Now, of course, we've done more. I mean, when we think about what we've done with surfaces, we do all these kinds of things with distances between points and some things about angles and areas and so forth. And those notions require some notion of distance, some notion of geometry. And that's not present with a surface, surface without geometry, of course. Now, if you add, in addition to this structure, if you insist that there's something called a metric on the surface, that gives you what's called a geometric surface. A geometric surface is an abstract surface paired with a point-wise assignment of an inner product. So a metric is a function from the tangent space across the tangent space to the reals, and that assignment has to be smooth. What does that mean? Well, that means that if you take the metric and you feed it a pair of smooth vector fields, out pops a smooth function, although we don't typically investigate that smoothness too much in this course. It's there. That's what we mean by that. Anyway, so the metric, and here's the notation, GP of VW is angle brackets VW. So this is actually Langle and Wrangle if you're teching. Anyway, so beware that this usually doesn't mean the dot product for the curved geometric surfaces we consider in Chapter 7 and beyond in O'Neill. And this has to be an inner product. Now, what does that mean? Well, in case you forgot from linear algebra, an inner product satisfies these 3 lovely properties. First of all, it's symmetric. Second of all, it's bilinear. And third of all, it has this lovely characterization right here that the metric of a vector in itself is non-negative, and it's only 0 when you plug in 0. All right. Now this third condition can be weakened, all right, or changed or swapped out. And actually, conditions 1 and 3 sometimes are tweaked. And if you have a different structure on the abstract surface, you could end up with something called symplectic or Lorentzian geometry. All right. So there's a great book by McInerney, fairly recent, that starts with sort of an abstract manifold, and then he has different chapters which each put these different structures on it, and you can compare and contrast and sort of really see what the idea of a Riemannian manifold is versus a symplectic manifold versus a contact manifold. But the blank backdrop is kind of like our surface without geometry, just a set which has got some bijective correspondence of patches. Okay, so another comment while we're on this symmetry here, right, tells you that the metric is not a differential form, because the differential form is antisymmetric, right? So the metric is actually a symmetric tensor, rank 2 symmetric tensor, and so that's an important distinction. And yet, we'll be able to do things with differential forms, despite the fact that, of course, the metric is not a differential form. One other comment while we're on it, come on, is if we were to replace R2 with Rn, you get an n-dimensional Riemannian manifold. Yeah, okay, modulo some topological comments. Different folks take different starting points for the manifold definition. Some people start with a Hausdorff space, which is a topological space, which is Hausdorff, and a few other locally Euclidean, a few other this and that. There's some excellent books written on the nuances of that definition. If you look at Lee's topological manifolds book, it's really quite in depth. Or Conlon, Conlon's differential manifolds got a lot on the topological preliminaries of manifold theory. But anyway, that's for another day. Again, a Riemannian manifold is basically a set which locally looks like Rn, and you have a metric which is an inner product for each point in the space. So you might be tempted to think, well, why aren't we calling it a Riemannian surface? Well, the reason we're not going to do that is because Riemann surface is a term which is already taken in complex analysis. All right. So anyway, some notation. We can define, of course, the length of a vector and the angle between vectors in the tangent space of a geometric surface in the same way we did. We just replaced dot products with the new metric, right? And there's also all kinds of really snazzy new ways of creating new metrics from old. For example, if you take the plane, all right, and you just basically divide by this so-called ruler function squared, then this gives you a new metric for the plane, or some subset of the plane, as is often the case. And this defines a geometric surface M that's said to be, this is just terminology, but conformal with ruler function H. So locally, every geometric surface is so expressed. So basically, there's some way of looking at an abstract geometric surface and just isometrically comparing it to some subset of the plane with some bizarre ruler function. Okay, we'll see some of that in practice as we go on here with some examples. Maybe not today, but eventually. The pullback metric is a great construction. Now you're like, wait a minute, you pulled back differential forms. You said the metric's not a differential form. How can you pull it back? Well, I can do the same thing we did for differential forms, right? So if I have a function f going from m to m, all right, a regular map, then because I need that in order to maintain that condition 3, that 0 is the only thing that has metric of, something with itself being 0, I need that regularity in order to be sure I get axiom 3 for the metric here, for the new metric. So again, suppose you have n as a geometric surface, which means that it has a metric on n, as in n, and I want to build one on m by pulling it back through this regular map f. So the definition for the metric on m, you just take the vectors on m, push them forward to corresponding vectors on n, and take the metric on n to evaluate what happens there. Or if you like g, I used where I had g as a more, g is the metric on n. I just notation, whatever. But so that's the pullback metric. Bilinearity is clear from the linearity of df paired with the bilinearity of g, and it's symmetric, it's positive, the positive definite, which is the third condition, by the way, also transferred directly from the metric on n to the new pullback metric on m. So here's a notation you might use for that. The metric on m is f pullback g. Again, extending the pullback to the context of symmetric tensors, we can do that here. Of course, I would lose other properties about pullback that we have said before about like wedge products and stuff like that because, well, I don't have wedge products. Okay, duh. Anyway, so note, this is equal to that. Hence, what that means then is what? That means that we have an isometry between m and between n. In other words, m with the pullback metric is isometric to n with the metric g. And so you're like, well, you only defined that for surfaces in R3. That's true. But pretty much all the definitions we gave for subsets of R3 have natural modifications to definitions here, right? So two geometric surfaces are isometric if there's an isometry between them. And an isometry between geometric surfaces simply means that the dot product, the metric is preserved, because we don't have dot product now, we have metric, the metric. So the metric on m goes to the metric on n in this case. All right, moving along. So another way you can build a metric is simply by, before we calculated E, F, and G by taking the dot product of XU and XU, or XU and XV and XV and XV, where that's the dot product in the ambient three-dimensional space. Well, we're not in that context anymore, right? XU and XV are not they're not three-dimensional vectors necessarily in this context. So, but you can just define, all right, the metric of xu, 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 xv, xv, xv to be ef and g respective, where these are particular given functions. And if you do that, and if these functions have the right kind of properties, like, for example, e.g. greater than f squared, then, voila, that gives you a metric. So we can actually build metrics with this prescribed e, f, and g by just working this backwards. Sorry, I'm covering up a irrelevant comment. So anyway, you can see exercise 4 for some indication on how to do this, although we'll actually put this into practice before too long, if not in this lecture, in the next. So we now work on describing how intrinsic calculus on a surface in R3 naturally carried to defining geometric objects, frames, connection form, curvature, and so forth on the geometric surface, remember, which is abstract. We don't have definitions there yet. It's very natural. So to start with, first order of business, the frame field. So a frame field on a geometric surface consists of orthonormal vector fields E1 and E2 defined on some open subset of M. And so, you know, you can still define the tangent space as the union of all curves or as derivations on functions, whatever floats your boat. And so you got tangent spaces at each point, and you can define orthonormal because you got a metric, so there's a notion of perpendicular, right? And there's a notion of length 1. So the orthonormal frame fields still have the metric of E1 and E1 is 1, the metric of E2 and E2 is 1, the the metric tensor acting on E1, E2 is 0, so they're orthogonal. They're metric orthogonal, right? So if the metric was G, I would say they're G orthonormal. All right. So if I have two different metrics on a space, they don't necessarily just describe the same geometric surface. The same point set with different choices of metric are actually different geometric surfaces in general. So dual frames are also defined as similar to as we did before. So once you have a frame field, you pick out the coframe or the dual frame by this this duality condition here, right? And so basically all of those formulas we had for components of forms and vectors are going to work out the same. The linear algebra works out the same, so we're still going to have like component expansions of one forms and vector fields just like we did before. And of course we can talk about the frame on some open subset of a geometric surface and so forth. We don't have to have it for the whole thing. We could talk about a frame on a subset of a geometric surface just the same. So finally to something with some meat and potatoes here. Given the frame E1, E2 with coframe theta 1, theta 2, and this metric, so it's a geometric surface, we define the connection form omega 1, 2 implicitly via the structure equations. D theta 1 equals omega 1, 2 wedge theta 2, and d theta 2 equals omega 2, 1 wedge theta 1. Now, this actually, I think I should say omega 2, 1 is equal to minus omega 1, 2. I haven't thought about it too carefully. I may or may not need to say that. Sorry, I'm trying to decide if that's a bee or a fly. I don't want to get stung. I'm wearing a bright red shirt. Oh well. I will move on. I will suffer the bee for the math. All right. Hopefully these are not foreboding words. All right. So to be explicit, the 1, 2 form, and I think this is almost the same calculation we went through before, but omega 1, 2 has this coframe expansion. So when you take the wedge product of this with a theta 1 and this with theta 2, the theta 1 and the theta 2 terms respectively collapse because theta 1 wedge theta 1 and theta 2 wedge theta 2 is 0, and it just leaves me with this is equal to minus d theta 2 and that's equal to d theta 1, which then says that omega 1, 2 is given by the theta 1 coefficient is the exterior derivative of theta 1 acting on E1, E2. The coefficient of theta 2 for the 1, 2 connection form is the exterior derivative of theta 2 acting on E1, E2. These are the formulas we found before. And the calculation is the same. So, that said, there's a question which is begged by all this, which is the coordinate dependence of theta 1 and theta 2. Now, before we were doing everything with respect to this universal backdrop of this, Cartesian coordinate frame that was there to do things, now we've lost that, and we're doing things on this kind of like, you know, coordinate system that we invented on this abstract set, and so it begs questions like, well, what if you invented a different coordinate system? How do you know what you're calculating isn't just a consequence of this coordinate system you just made up on this, you know, abstract set of two-dimensional matrices or whatever? So it's an important question to investigate is, you know, do our constructions have coordinate dependence? In other words, if you had another frame, E1 bar, E2 bar, and another coframe, theta bar 1, theta bar 2, how would the 1-2 bar connection form relate to the original coordinate systems form? So since we're in 2 dimensions, the coordinate relation is relatively simple. You can picture it like this. It has to be that there's some angle that rotates from E1 to E1 bar. We'll call that angle phi. And since they're both orthonormal, this frame has to exist. I mean, you can work it out. It basically, because they're both orthonormal, there has to exist a theta, a phi, such that these equations hold. Now, you can work that out. I haven't worked that out here, but that's just a matter of some linear algebra there. But E1 bar is cosine phi E1 plus sine phi E2, and likewise for that. It's a rotation by angle phi, right? And that is rotation angle phi in the sense of angle for the metric, all right? It's the metric angle, the angle as defined by the metric. Okay, so of course you have a choice. You could either go with the blue one or the red one or the blue one. For your, once you have E1, you could either take this to be E2 bar or that to be E2 bar. So there is a different, you could go 2 different ways here to get, once you pick E1, you have 2 choices, right? And one of those is said to be positively oriented and the other one's negatively oriented. The blue is negatively oriented, the red is positively oriented in the sense that the red shares the same orientation as the brown original frame, whereas the red blue frame has opposite orientation. Here, orientation in 2 dimensions basically is understood in terms of, do you get the second from the first by just a counterclockwise rotation, right? All right. So let's look at it. So here's the lemma. Lemma 1.4, if you've got 2 different frame fields, and then the 1-2 connection form of the different frame fields actually doesn't have to be equal, but the difference, you know, the distinction between the 1-2 connection form is really, it's very beautiful. It's simply given by the sum of, it's the exterior derivative of the angle function, like that. And if it's got the opposite orientation, then it's minus omega 1-2 plus the exterior derivative of the angle function. And in the case of same orientation, the wedge product of the 1-2 coframes are the same. Whereas if the opposite orientation, you get a minus here as well. All right, this will become important. Both of these minuses come together to conspire to show you that the Gaussian curvature doesn't care about the orientation of the frame a little bit later in this lecture. Or maybe that's next lecture, I forget. But anyway, here's the proof. So here's your relation between the barred frame and the original frame. And as usual, I think I can, let me just, all right, let's see if I can fit this here. Then, of course, I can expand theta 1 and the barred theta 1, bar theta 2, like that. But if you look at theta 1 of E1 bar, then let's see here, that would be, how do I know that that's cosine phi? I know that's minus sine phi. Huh. Well, so theta 1, oh, sorry, theta 1, E bar 2, and, all right, let me see if I can work this out here. So let's focus on this one, theta 1, e bar 1, right? So what happens when theta 1, so you take e bar 1, right, and put that in place of e bar 1, this right here, right? Now theta 1 hits e1, and it just gives you back 1. So that's why there's a cosine phi here. On the other hand, the theta 1 hits e2 and gives you 0. That's why there's not a sine phi here. Over here I have theta 1 e2 bar. e2 bar, well, theta 1 act on e1, it gives me a minus sine phi. There it is, and this piece drops out. Now down here, I've got theta 2 and theta 2, so that picks up this term and that term respective. See it? All right, nothing too mysterious. All right, so you can calculate the wedge product, theta 1 wedge theta 2, and so we can express that in terms of the barred theta, the barred coframe, right? Or dual frame if you prefer. And you take the wedge product. Theta wedge itself is 0, so you got like theta 1, theta 2, theta 2, theta 1, but you have to commute the order, so you get a minus there. Cosine squared plus sine squared, well, we know what that is. It still matters, it's still 1, so there you have it. Now, that assumed the positive orientation, the negative orientation through very similar calculation gives you a minus there, all right? And also the exterior derivative, if you calculate exterior derivative of d theta 1, d theta 2, you know, exterior differentiating the formulas that I just took off page, but you get these lovely formulas here, because to exterior differentiate theta 1, you have to exterior differentiate this, right? So that gives you like the, you know, like minus sine phi d phi theta 1, and then plus cosine phi d theta 1. There's 4 terms from the product rule in this and the product rule in that, right? And so that's what we see down here. Those 4 terms, and then of course 2 of them involving d theta 1 bar, d theta 2 bar. But remember, d theta bar 1 and d theta bar 2 can be expanded. I don't know if I do that here though. Oh, okay, and then this again, same thing there. But d theta bar 1 and d theta bar 2 can be written in terms of the 1-2 connection form by the structure equations, right? Which have become the definition at this point. Now, and so I'm calculating, and I'll continue calculating on the next page, continuing. So here's the complete thing. So d theta 1, I should have just flipped over to here, I'm sorry guys. This one's, page 6 is clear, although it's still probably too lengthy. The calculation, if you look at it in O'Neill, is pretty slick. So this is, you know, less slick, but probably more what most of us would end up doing. So anyway, I've collected together the terms that come from differentiating with respect to phi. Over here is the d phi bar, d theta bar, the d theta 1 bar, d theta 2 bar terms. Of course, these we can convert to the 1-2 bar connection forms because of the structure equations, and you can recognize that when you group the derivative terms together, you get theta 2 again, so that's theta 2, and on the other hand you get this and that. But if you factor out the omega 1 bar term, you get this, all right, but that is exactly theta 2 again, so you got theta 2, you got theta 2, you got d phi, you got omega bar 1, 2, and so when you factor out then the theta 2 using the properties of the wedge, it gets me a minus because I had to change the order, right? I get d theta 1 is omega bar 1, 2 minus d phi, wedge theta 2, which is, you know, pretty nice because that's what we were, well, it's almost what we were trying to show. Let's see here. And on the flip side, let me see here if I can complete the thought here. I'll do it in orange. Let's see here. We used it up here. Let me see if I remember the pattern. So like d theta bar 2, right, is omega 2, 1 wedge theta 1. So d theta bar 1 should be equal to what? D theta bar 1 should be equal to, for example, should be equal to omega, let's see here, I think it's 1, 2 wedge theta 2, right? Now I've been putting the 2 upstairs, so sorry. I probably should put it downstairs to be consistent with this lecture, but oh well. And we're gonna find this same relation when we go through the similar calculation for the other piece here, d theta 2. We end up with omega bar 2 minus d phi wedge theta 1. So that would be equal to omega 2 1 wedge theta 1, right? And so when you have both of these orange equations being satisfied by a certain form, this one, right, then it follows that omega 1 2 is equal to theta bar 1 2 minus d phi, which is precisely what we wanted. You think I thought it was a plus. Well, but in the original, back in the lemma, we had solved for the barred connection. So like, see, we solved for the bar. So it's, if you subtract d phi to the other side, it's the same equation. All right, and a very similar calculation will show the conclusion for the oppositely oriented frame. And but it's a very beautiful equation in terms of coordinate change, because basically it shows that the choice of frame is just tied to the choice of angle. All right, and because you get 2 dimensions, so like, you know, you get a 2-dimensional set, you have to pick a direction, right? And so what's your freedom in choosing a frame? It's just what direction you pick. So you pick this way, you pick that way, but anyway, it's, you know, it's just a question of angle. That's the freedom you have in your choice of frame at a point on a surface. All right, so that concludes what I have to say about section 7.1. We'll move on with section 7.2 next. Thank you.